Alright guys, this is our last objective. It's over exponential functions and equations. There are two types that you have to be able to recognize. That is exponential growth and exponential decay. See how the graphs, if it's growth, it should be increasing from left to right. Decay should be decreasing. Another way you can tell is if it's a growth, that means the b in the form is greater than 1, versus for decay, the b is going to be between 0 and 1, so it would be a fraction or a decimal. So parts of this is our standard form for an exponential function. The parts are your a here, that's the beginning amount. It's also your y-intercept. And then your b, the b here, that is your growth or your decay factor. Okay. Now another part you have to know is your horizontal, your asymptote. Your asymptote is basically where the graph here starts to flatten out. Okay, it flattens out, but it never crosses. So oops, sorry, gonna do that. Where the graph turns, where it flattens out. Okay. All right, so that our asymptote correlates with our range. So it's important we know the asymptote because it's going to help us determine our range. So if this flattening line out is, I'm just going to put HA, horizontal asymptote. And since this graph here of decay, but this curve here is above that horizontal asymptote, then it's going to be y is greater than or equal to whatever that value is. Or here, it's going to be 0. Same thing, this is going to be greater than or equal to. Now, if the graph is below the horizontal asymptote, and we'll see an example of that, then it would be less than. Most of these exponential growth or decay problems are dealing with interest rate. So another key thing is for growth, we should see increasing, and that increasing is 1 plus the percent. So it's going to be, b should be greater than 1. And that's kind of said already here when I said b is greater than 1. If it's depreciating or decreasing, this is when we're doing 1 minus whatever the percent is. Now we always write that percent as a decimal, okay? And that's just an example. So we're going to finish this up by looking at an example here. Here is our equation of an exponential function, right? That's given to us. Here is our scenario. It says the population city is increasing at an annual rate of 4.5% when the increase began at the population of 1800. So we first have to, R must be written as a decimal. So this percent as a decimal, remember you move your decimal 2 places to the left, is 0.045. So our A is our initial amount, and our initial amount in this problem is the 1800. Okay, the meaning basically for that is this represents the starting population here. This is our starting population. I'm just going to abbreviate that. Now R is our rate of growth. This is our decimal that we have, or that I was showing over here, which is 0.045. The B, the growth factor, is when I'm adding here to that initial rate. So if I did 1 plus 0.045, that's just going to be simplified as 1.045. Okay. And so this is basically the population multiplies our population. Multiplies, and I'm going to abbreviate that. It multiplies by a factor of 1.045. 0.045. So basically we want us to put it all together, write the growth factor right here. So if I was going to write the equation, just plug in the parts, we have y equals the initial amount, which was our 1800, sorry, that's our A. In parentheses, we have our 1 plus our 0.045, close the parentheses, to the x power. So there is the equation. Now they want us to predict the population in 5 years and 10 years. So we have to put this equation in our calculator, which is what they're showing you over here, okay? So you put it in the calculator and then you go to your table. So our prediction after 5 years is right here. This is our x is our number of years. So we can say that prediction is 2,243. Or actually 0.1, so we're going to round that up. You can't have a point of a person, so let's say 44. And then after 10 years, which is showing down here, we can have 2,796. Okay. So you just have to be able to remember how to put it in this form. This part is not on the form chart, but this is. So if it's growth, you just got to remember we're adding 1 to that decimal, versus if it's decay, you are subtracting the decimal from 1. So I believe, let me see right here. Yeah, here's an example of a decay problem. So a new van sells at 25,600, depreciates, that's another keyword showing decay, at a rate of 15%. So the initial amount is the 25,600. The meaning basically is this is how much the van was worth when sold. Okay. Value of van. When sold. Sorry. Our rate, our decay rate is this percent as a decimal. So this would be 0.15. Our growth factor, or decay factor, sorry. This is when we take the 1 and minus that decimal, 0.15. So this comes out to be 0.85. So this is going to get multiplied by a factor. That's factor, guys, of 0.85 each year. Okay. All right, so we're going to write an equation here. Our equation would be taking our initial amount, 25,600, now 1 minus the 0.15 to the x power. Now they want us to predict the value after 3 years, 5 years. So we have to put this in our calculator. So we want to go to our y equals. I'm going to clear this out. We're going to put 25,600, then parentheses 1 minus our 0.15, close the parentheses, to the x power. And we're going to go to our table to figure out the value after 3 years and 5 years. So I'm just gonna air it down. We don't need that negative. That's no such thing. So after 3 years, the car is only worth 15,000. I'm just gonna double check something real quick. Yeah, so that does give us the decimal. So you can highlight it here. So we get $15,721.60. Let's record that real quick. And then after 5 years, you can look back and come down 5 years. There is our value. So we're going to have 11,358.86. Okay. All right, so you might have a word problem asking you to come up with these values, come up the equation versus when it's an exponential growth versus decay. So you do need to know those key information. And then Excuse me. You might ask to be graphing a scenario. So in this example, we know that there's initial amount of 20 bacterial cells, and after 1 minute, there's 30 cells, and after 2 minutes, there is 45 cells. So, kind of help you see this, what's going on here, I'm just going to kind of create this little table down here. So the initial amount is 20, then 1 minute, it's 30, and 2 minutes, sorry, it's 45. Now, because we're looking for exponential change, it's not linear. So in other tables, we would normally say, okay, that increased by 10, and then that increased by 15. Okay, so what's happening is this is not a constant rate of change here, because it's not the same amount. But what we could do is figure out the multiplier to get this. Okay, so let me just, oops, I didn't erase everything. Hold on, sorry. So we can maybe see this better using our graph here. If I look here, I'm going to make, this is just our time, and this is the amount we have, the number of bacteria. I'm going to put time here, and then bacteria here, the number. So if I can like show, instead of doing each increment, I'm going to do 0, then 1, then 2, then 3. And I'm going to do my increments here. Let's go 5. Yeah, increments of 5. I think that'll work. So 5, 10, this is 15. 5. Alright, so our initial amount was at 20 at 0. So that's starting right here. Then at 1 minute, we went to 30. So that's here. And then at 2 minutes, we are at 45, which is here. So we're trying to get you to see that this is an exponential graph. And then here, from getting that graph, we can answer our questions here. So they want us to find the x-intercept. Well, basically, that's where if x is 0 right here. This is x-intercept, y-intercept, sorry. So y-intercept is at 0, 20. And what does this mean? Basically, it's the initial amount. To interpret, this is the starting amount of bacterial cells. Your asymptote is where it's going to flatten out. Okay, so we kind of don't see this here, but this graph's gonna eventually flatten out here. Sorry. And so it kind of, this one it's not gonna apply because we don't see where the other part here. So I'm gonna put does not apply. You can't really, I mean, I can guesstimate that it might happen like maybe at 15, but I don't really know, so I can't really answer that. Our range, our domain, we know is for this graph is where it starts. It starts at 0 and it keeps going. So it's x is greater than or equal to 0. And our range starts right here. So let me take this part because this doesn't include in the graph. Our range starts at right here at 20 and then keeps increasing. So this is y is greater than or equal to 20. Okay. So on this one, they give you the graph. They want you to come up with the A, the initial amount. And hopefully you can see that the initial amount is going to be the y-intercept right here. So that's going to be at 10. Okay, so we had basically 10 cells to start with. Our B, this is our growth factor, like how is it changing? So what I would need to do, this is a 0. I need to see here, there's a pattern. This is 20, and then at 2, it goes 40, and 3, it goes to, well, 3 actually goes here to 80. So if you notice, if I double 10, I get 20. If I double 20, I get 40. If I double 40, it goes to 80. So it looks like it's doubling every time. So that would be my growth factor is 2. So this basically is that the number of cells double each day. So my equation here would be y equals the initial amount, which is a 10, times the growth factor, which is 2, to the x power. And then I could use that to find some more values at a certain time frame. Okay, so this kind of goes over our exponential right there. Please make sure you take the time to look at your flashcards, especially the day before the test. You know, if you have more quizzes to finish because that's your average score that you need to get, then yeah, do some practice problems. But I really would probably focus on just flashcards, facts. Don't, over prepare. I really want y'all to have a good night's sleep. Look through the packet maybe, but just test your knowledge. What have you retained? So I would maybe more focus on your flashcards for the night before. And do practice problems only if you're not done. All right. Thanks, guys.